We are very pleased to have Satoshi Yamaguchi from Osaka University. He will tell us about this non-invertible topological defect in four-dimensional gate theories. So Satoshi, please.
Thank you very much for the introduction. And I would like to thank the organizers for inviting me and giving me this opportunity to talk. Today, I would like to talk about non-invertible topological defects in four-dimensional Z2 pure lattice gate theory. And this talk is based on the collaboration with Masataka Koide and Yuta Nagoya. And both of them are excellent students in Osaka University. And the paper will appear in PTEC. Okay, let's start with the introduction. Today, I would like to tell you something about the recent development of the symmetry. And symmetry is a quite fundamental concept, and it's very established and quite well written in the textbook. But in addition to such traditional symmetry, recently people talk about something new symmetry, which was not called a symmetry previously, but people find that such thing will be useful as this traditional symmetry. And today I would like to talk something about this new symmetry. And before going into the detail, let me talk about some motivations or applications of such new symmetries. And symmetry plays an important role in everywhere in physics, but today I would list only 3 of them. And the first one is a phase structure of quantum field theory. And this is the biggest achievement or using this new kind of symmetry. And starting from these seminal works, there are a lot of excellent results about the phase structure of the quantum field theory using these new symmetries. And symmetry plays an important role also in the string theory. And such new kinds of symmetry are investigated in the string theory by a lot of papers, including these papers listed here. And also, I listed here the physics beyond the standard model or phenomenology. And phenomenology people often talk about naturalness, and which is roughly speaking fine-tuning without symmetry. And so if the concept of symmetry is extended, then such it should be affect to the notion of naturalness. And so far, I don't know much about the phenomenology papers treating this new kinds of symmetry, but I bet this direction is quite important. And among these new symmetry, today I would like to talk about so-called non-invertible symmetry. And this non-invertible symmetry does not have any group structure. And in that, any traditional symmetry is always associated with group. But this non-invertible symmetry is not associated with any group. So in that sense, this is not a symmetry in the traditional sense. But at least in 2 dimensions, this non-invertible symmetry is quite proved to be useful. And and they are investigated by many papers. And yesterday, Kikuchi-san's in Kikuchi-san's talk, he used something about, he told us something about this two-dimensional non-invertible symmetry. And but in higher dimensions, such non-invertible symmetry is not well understood than compared to the two dimensions. And it is partly because there are not much examples in 3 or higher dimensions, not much examples of non-invertible symmetries in higher dimensions. So that's what I would like to address today. And in my paper with Koide and Nagoya, we find a new example of non-invertible symmetry in 4 dimensions. We studied 4-dimensional Z2 lattice gauge theory. And this Z2 lattice gauge theory includes so-called one-form Z2 center symmetry, which is also a recent new symmetry. But this is rather mild generalization. And this one by itself has some group structure, this group Z2 structure. And this 4-dimensional Z2 lattice gauge theory also has duality. And this is similar to the 2-dimensional Kramers-Wagner duality or 4-dimensional duality, electromagnetic duality of the Maxwell theory. And duality is quite similar to the symmetry, at least at the self-dual point. But what we found is this duality is not a symmetry in the traditional sense. And this is actually so-called non-invertible symmetry. That's what we found. And in addition, we also find the algebra with quotation mark of this non-invertible symmetry. Non-invertible symmetry does not have any group structure or Lie algebra structure. So the algebra has quotation mark, and but there is some analog of certain commutation relations or something like that, and that's what we find. And I would like to emphasize that this symmetry will not be only a special symmetry of a special theory. We only consider one single theory and find this symmetry, but it appears in many theories, at least we expect. And more recently, some people have found similar symmetry will appear in many continuum theories. And later I will mention about those works. And in the development of this new concept of the symmetry, this topological defects play a quite important role. And in this talk, I also talk how this topological defect is related to the symmetry. And actually, symmetry is always associated with some kind of topological defects. And this is first pointed out by this seminal paper. And they use this picture to extend the symmetry, that concept of the symmetry. Okay, so this is a plan of my talk. And first, I want to explain how this symmetry is related to topological defect. And then I want to explain those generalized symmetry. in particular, non-invertible symmetry. And next, I want to explain our own works. And finally, I will give some summary and some discussions. Okay. So first, I would like to explain how this symmetry is always related to topological defect. So let me start with a quite common definition of the symmetry. And in the textbook definition, the symmetry is some transformation which leaves the action invariant. And usually, we derive some relations between correlation functions and use what I meant is, for example, Ward-Takahashi identity. And use that relation between correlation functions. We study quantum field theories using these symmetries. And even if you don't know this part, you can start from this one and say a lot of things. And let's consider these relations between correlation functions. And I listed here two types of correlation functions. And relations between correlation functions. And the first one is what I would like to call a global form, which is also sometimes called Ward-Takahashi identity. And if you transform all the fields in the correlation function, then the expectation value does not change the value. The expectation value of both sides has the same value. That is quite simple relation, and it's already quite useful and constrain the correlation functions. But more convenient one is a local form of the Ward-Takahashi identity. And this is usually called what we call Ward-Takahashi identity. And this equation, if the insertion of this divergence of current is not coincide with other point, then this is just divergence of the current is 0. And if this divergence of the current insertion point coincide with other point, then this relation gives you the transformation of the field. This is our Ward-Takahashi identity. And this second form is, in general, much more convenient than first one. Okay. It's simply one reason, the convenience of this, one reason is just you can focus on one local operators or one local region of the space-time and forget other part. Transform only this operator. So that's the one reason that this is more convenient than this one.
Excuse me, I have one question. So,
yes.
So do you always have local form even for discrete symmetry?
Yeah, that's what I would like to address. So one disadvantage, thank you for the question. And one disadvantage of this local form is we do not have such, this is, because this is for infinitesimal transformation, we do not have any local form for discrete symmetry. At least it's not written in the textbook. So what I would like to address here is there is some local form for discrete symmetry or disconnected group symmetry. And the answer for this one is the topological defect. And that's one of the biggest motivation to introduce topological defect in order to use those symmetries. Okay, anyway, let's try. So to be very concrete, I would like to use this Ising model example. And we put spin degrees of freedom at each site. And the partition function is this form, and the action has this form. And the interaction is put on each links. And this model has this Z2 symmetry, discrete symmetry. And what I would like to explain here is how to write down the some local form of the Takahashi identity for this Z2 symmetry. Okay. So the strategy is the same as the derivation of usual Takahashi identity. We apply the space-time dependent transformation, although this is a global symmetry, but we apply space-time dependent transformation. We choose some region D, arbitrary region D, and consider this kind of transformation. Within region D, the spin is flipped. But outside of region D, just we do nothing. Let's consider such transformation. And see how this partition function is written. And the first step is nothing. We just rewrite a sigma with sigma prime, just change the letter. And the next step is substitute this one. One advantage of this lattice picture is it is very clear that this measure part does not change by this transformation. This is one-to-one mapping, so the measure does not change. And but of course, this is not a symmetry in the narrow sense. So the action changes because we only transform part of the space-time. But I would like to see they are different, but how they are different. What's the difference? And if the link, the interaction is at a rich link, or the Lagrangian density is at a rich link, and if the link is completely outside of the region, then of course we did nothing, and it does not change this way. And if link is completely inside the region D, again the Lagrangian density or interaction does not change because both of the sign, both of the spin is flipped. Then the total sign does not change. So this is because this is originally a global symmetry. So if you only look at this link, for example, it does not change. The problem is link at the boundary of D. And one of the site is outside of the region, and the other site is inside the region D. Then the interaction changes. Here you have extra minus sign, and we express this different link by this red link. And it should be called something defect, because defect means something incomplete or something some impurity or something like that. And away from this boundary, then everything is quite homogeneous. But these links are different from other links, so it's different from other parts. So it's in some sense it's not complete. So we want to call such place defect. And this defect is derived from symmetry. So let's call such a kind of defect symmetry defect. Okay. So there are symmetry defect here at the boundary of the region D. So let's see the equation what we derived. The partition function is equal to the say partition function with this defect inserted. In the equation, partition function is equal to the partition function inserted this defect, and this defect is written as this way. But only the difference is localized at the boundary of D, which is denoted by sigma. So this is kind of a codimension 1 surface defect. And if you divide both sides by partition function, you will get this equation. This is one of the, I would like to claim that this is one of the Takashi identity derived from this symmetry. And it's kind of similar to the conservation law of the divergence J equal to 0 relation. It's something analog of that relation. And then what happens if some other operators are inserted? If other operators are not inserted inside this region D and only outside, then the story is completely the same. You flip the spin only in this inside region D, then you will get this symmetry defect at the boundary of D, and it's completely parallel to the previous one. And if some operator is inside the region D, then if you flip the sign of this inside region D, then the sign of this one is also flipped. So this is transformed by that manipulation. So I would like to claim that this, in particular this one, is a local form of the Takashi identity. And for example, if you apply the same thing for the continuous symmetry, then your familiar Takashi identity can be derived from this one. And oppositely, starting from your familiar Takashi identity, you can easily derive this one. This is what you do often do in the conformal field theory in 2 dimensions, but for such procedure can be done for any dimensions. And but the difference from the familiar Takashi identity and this one is this one can be applied to any group symmetry, a discrete group symmetry, or say disconnected group symmetry. So this is a big reason, biggest one of the biggest motivation to introduce such topological defect to study the symmetry. Okay, let me summarize the properties of this ordinary symmetry defect. And the first one is it's topological, and if you apply the transformation for this one, then this region changes to this one without changing topology. And we divide such thing into two parts, topological and invertible. And the next one is quite similar to topological, but a bit stronger condition. And the expectation value is the same if the difference is a boundary of a region without any insertion. Means, let me explain what this means. And by this one, the difference of left-hand side and right-hand side is this one. And this one is region, a boundary of this region. And this region, there is no insertion. So in that case, you can just eliminate this one and get this one. And this one is similar. This handle is some region, boundary of some region without any insertion. And so you can put handle here without any, without changing the expectation value. And first one does not change the topology. And second one, sometimes the value does not change even if you change the topology. Okay, this one different, has different topology, and this one a different topology. So invertible is a stronger condition than topological. And the final one is codimension 1. And because we obtain such symmetry defect at the boundary of the region D, so it's codimension 1 for ordinary symmetry. So this oppositely, if you have such topological defect, then you will get symmetry in the traditional sense by defining the transformation by this. Transformation by this equation.
Excuse me, may I ask a question?
Yes, please.
So in your topological case, can you define a generator or current for your symmetry?
Yes, if this is a continuous symmetry, this, for example, this insertion is replaced by some exponential of current inserted on this one. If it's continuous case, this Q is some sigma of just a current J, something like this, and this one is exponential. The some parameter alpha Q. But for this, we want to apply such local form to discrete case. There's no currents for discrete symmetry. So that's a motivation to write down such fancy notion of topological defect.
Okay, thank you.
Okay.
Okay. In the derivation of word cache identity, did you assume absence of anomaly?
Could you say again? What?
In the derivation of word cache identity, did you assume absence of anomaly?
Yes, we assume. In this Ising model case, it's apparently in this example, it's apparently there's no anomaly, and in generically we assume there's no anomaly. If there's anomaly, then there should be some modification.
Okay, thank you.
Did I answer your question?
Yes, thank you.
So
Can I ask a question?
yes.
So if we take particular critical limit, we have some C equal 1/2 CFT
Right.
written by minor. Can we express write down this your operator, your action, topological action, by in terms of this field theory language, twist operator or minor fermion?
It's not quite explicit like that one, but that is called a Feringe line, and correspond to this operator. It's Feringe line, and for corresponding to the energy operator.
Energy operator.
Yes.
Feringe line for energy is related to fermion.
Yes. Psi bar or something like that one, but it's local operator, and Feringe line is something like the monodromy of that operator or something like that. So it's not quite explicit like that one.
Non-trivial changes conformal blocks.
Yeah, that one.
Very non-local. Thank you.
And yes, as well, I don't know how. I don't know whether we have explicit representation of that one. Okay, here is a technical remark, and we use this strange link, but it's more convenient to use, instead of this link, use this link. Divide this vertex into two, or we double this vertex and connect by this pink glue, and assign this weight to this connection, or this part, and this weight force this side, this spin and this spin has opposite value. Then this configuration and this configuration has the same weight. And for example, if some those defects are connected like this way, then it's replaced by using this spin glue by this way. And this is quite technical, and it's quite convenient, but it's quite technical, so you can forget this one. So this is the end of the explanation, how the symmetry is related to the topological defect. The biggest motivation is that we want to write down the local form of the Wata-Kasha identity. So let's consider the generalization of the symmetry. So far, the symmetry is always associated with topological defect. And so how about this way? Does arbitrary topological defect always associated with some symmetry? And the answer is no. Topological defect is not always associated with symmetry. So, however, we can write down Wata-Kasha-like identity, which is not associated with symmetry, but for any topological defect, you can write down this kind of symmetry because this defect is topological. You can shrink arbitrarily, and this situation is same, must have same effect as the local operator. And so in that sense, such arbitrary topological defect, which is not associated with symmetry, but it can have the same, it can be used as the same way as the symmetry. Okay, any topological defects should be able to be used in a similar way to symmetry. So let's consider such non-symmetry topological defect. And there are two additional properties in addition to the topological. First one is codimension 1, and you can generalize it to codimension q plus 1. And this is rather mild generalization of the symmetry, and this is called Q-form symmetry recently. And another property is invertible, and you can generalize it to non-invertible one. And this is more drastic generalization of the symmetry, and that one I would like to call non-invertible symmetry. And this is just another name of general topological defect. And this is a main topic of my talk. And non-invertible symmetry has the following properties. It should be topological unless it's very difficult to use the same way as the symmetry. So if you continuously deform this one without changing the topology, then the value does not change. That's topological. And non-invertible means if you change the topology, the expectation value may change. So this one may not be equal to this one, and this one may not be equal to this one. In particular, this circle or sphere expectation value may not be equal to 1. In other words, if circle expectation value or in 2 dimensions, it's often called quantum dimensions. And if it's not equal to 1, then the associated symmetry is not a traditional one, but it's a non-invertible symmetry, something new. Okay. And
sorry, I have a question about this.
Yes.
So you're saying this circle is related to quantum dimension.
yes,
So that is non-trivial for rational conformal field theory.
Mhm.
Often. So that case, you have this non-invertible
right,
example
right.
also. But
right.
also, I think this Ising model
Uh-huh.
is the Mayonnaise fermion,
Mhm.
also has a non-trivial fusion algebra.
Right.
So still, but you're saying that is invertible.
Yes.
So what kind of case corresponds to non-invertible in this 2D?
2D Ising
Mm.
case. Let's soon. I will come to that point. But there is maybe 3 kinds of such topological lines.
I said because I say so. This is an energy operator.
Yes.
Previous that is a invertible.
Yes,
But if we
because
choose
this is
other
one,
one, then non-invertible. I see.
Yes.
I see. Thank you very much. Yeah.
Thank you for the question. So energy operator is, line operator corresponds to energy operator is invertible one, and it corresponds to these two symmetry. And the other one that corresponds to spin operator is not non-invertible, and it corresponds to the so-called Kramers-Wanier duality. That I will come in the next slide.
Excuse me, so I have a quick question. So,
Yes.
so when the expectation value of the operator is equal to 1, so
Mhm.
does it mean it is topological, ordinary topological defect?
Not always.
I
Even if so, in 2 dimensions, maybe it could be true, but in higher dimensions, it's not always. Even if some close with such thing is 1, it does not always mean it's invertible. In 2 dimensions, I guess maybe it's true. Quantum dimension is 2, quantum dimension is 1, it corresponds to invertible. Okay, so let's think about some example. And in 2 dimensions, there are lots of examples, what Tadashi mentioned. And what people have shown is that it is actually useful in two-dimensional quantum field theory. And some main papers, including these papers, have shown that such operator is quite useful to investigate the phase structure in two-dimensional quantum field theories. And what I would like to think about is that it would be nice to have such a tool, non-invertible symmetry, in 4 dimensions or 3 or higher dimensions. And the problem is we do not have a rational conformal field theory, and there is no straightforward generalization of this one to higher dimensions. So it's not an easy problem.
Can I ask you a question?
Yes.
Yeah, so I'm just wondering how this non-invertible symmetry can constrain the dynamics of the given system. Can you explain a little bit more about this previous work by Komagaskis and others?
Yes, for example, the most famous one is this one. And there is some relevant deformation of tricriticalizing model. Which breaks the Z2 symmetry or other symmetry, but only preserve kind of non-invertible symmetry called Fibonacci symmetry, which F square F plus something like this one. And if you have this symmetry, you can show that the combined with modular invariance, you can show that the because the eigenvalue of this such F must be irrational Golden ratio. So by using that one and the modular invariance, you can show that the vacuum cannot be trivially gapped. I mean, vacuum must be degenerate or gapless. And actually, this relevant deformation, this vacuum is known to be degenerate, and it used to be a mystery, and it's first found by Topological, but it used to be a mystery. It's not explained by any symmetry, but it's degenerate accidentally. But using this non-invertible symmetry, it must be degenerate. That's how one of the example.
Okay, so you are saying that this this fusion algebra, this relation should be preserved along the algebra flow?
Yes.
That's the idea?
Yes. Okay, thank you. That's the idea. So the such topological defect is invariant because it's topological, it's invariant under the RG flow. So it constrains the IR dynamics.
Can we also have notions of anomaly for this non-invertible symmetry?
I think so.
How?
Yeah, it's for example, in the anomaly in this picture is described by the some trivalent vertex. For usual symmetry, the anomaly is associated with, for example, the trivalent vertex. There is some non-trivial phase to this one, which does not satisfy this crossing relation. If you have some vertex phase then it's called anomaly because it does not satisfy this one, and you
I
cannot
see.
gauge this one. Yeah.
So each line represents the defect.
Yes, yes. Each line.
Okay,
represents
now
this
I
defect.
understand. Okay,
Yes.
thank you.
Okay. And the example, another example, this is one of the another picture of the same example, is a Kramer's one-year duality in two-dimensional Ising model. And this is an example of a line corresponding to the spin operator. But these people do not use the two-dimensional rational CFT picture, but use the lattice Ising model to investigate this Kramer's one-year duality. And they explicitly constructed a duality defect. And as I shown before, this is Z2 symmetry defect. And in addition to this one, they constructed this Kramer's one-year duality defect. I show here something, but I just want to show that this is quite explicit. And they calculate the circle expectation value or quantum dimension of this operator, and it's square root 2, and it's not equal to 1. So it must be the non-invertible symmetry. And of course, it is the same one as the quantum dimension of the spin operator, and as expected from the rational conformal field theory. And the point is that the approach does not depend on the rational CFT, and it's more or less straightforward to extend this approach to higher dimensions. And that's what we did. So I would like to explain a bit about our work. And we consider four-dimensional Z2 lattice gauge theory. This is an analog of two-dimensional Ising model. We just increase the dimensions. And this is nothing but Wilson's lattice gauge theory with gauge group Z2. And we put spin at each link, and consider such Lagrangian density. And for each bracket, we have this Lagrangian density, and sum up all the bracket. And this is Wilson's gauge theory for Z2 gauge group. And actually, this parameter K is related by gauge coupling, roughly related by gauge coupling by this way. So for large K, this is weak coupling, and for small K, this is in the strong coupling. And the phase structure of this theory is quite rather well known. And in the strong coupling regime, it's in the confinement phase. And in the weakly coupled weak coupling regime, this is in a deconfinement phase. And it's called some other names, but in particular, in the confinement phase, the center symmetry is preserved. And in the deconfinement phase, the center symmetry is spontaneously broken. And here, center symmetry is some one-form symmetry, which is a kind of a mild generalization of the symmetry. And this critical point is exactly predicted by using the duality. This is an analog of Kramer's one-year duality in 2 dimensions or electromagnetic duality in 4 dimensions. And it's found by Wegener in 50 years ago. And the self-dual point is should be a critical point by the same argument as a Ising model.
Can I ask a question?
Yes.
Can a trivial phase be exactly dual to a topologically ordered phase?
Okay. It's not completely, the same. Local by the local local expectation value, they cannot be distinguished. So it's in that sense that for the say thermodynamic quantities, they are completely dual. But some topological one, more precisely speaking, the duality includes the gauging of this center symmetry. So more precisely speaking, this trivial phase is dual to the topologically ordered this phase with this Z2 center symmetry gauge. That's a precise statement.
Okay, then this non-exactness of duality, will it affect your construction of non-invertible symmetry?
Right, exactly. That's actually the point. If duality is exact, then it should be invertible symmetry. And as in the, for example, the electromagnetic duality of Maxwell theory is an exact duality, and that is a group symmetry. Say, for example, SL to Z or something like that. But this one is not exactly the dual and slightly different. So that is a point. That's how we get the. That's why we get the non-invertible symmetry in this case.
Okay, so another question. Sorry. So if the duality is not exact, can you regard the duality defect as a genuine defect in the original theory?
Yes.
It appears that you are changing the theory across the duality defect.
No. We are not. Okay, so more modern or more recent way of language, it's called this way. At this value of k, the gauged theory and ungauged theory of this symmetry is the same because it's related by duality.
So locally the same, but not globally the same, right?
No. This duality relates gauged theory and ungauged theory.
Okay.
So the gauged theory and ungauged theory are the same. So the gauging, the manipulation of Z2 transformation, instead of the manipulation of Z2 transformation, we apply some gauging this symmetry. It does not leave the action invariant, but it gives you some kind of defect. And because the gauge symmetry is discrete, the defect is topological. But the gauging is not a symmetry of, in general, it's not a symmetry, so it may not be a symmetry defect. That's one way of.
Thank you. I think I understand. Yeah, thank you.
Yes. Okay, thank you very much. Yes. So I constructed a defect for this duality and this center symmetry. And I just show this one because I want to show this is quite explicit. And we constructed, we determined the weight for the building block of the duality defect and the center symmetry defect in this case. And also we determined the weight for junctions. And I would like to emphasize that we are working in the Lattice theory. So there's no mystery of continuum quantum field theory, no continuum limit or anything. So the result is completely rigorous. And we calculated this S3 partition function, S3 expectation value, and it's square 1 over square root 2, and it's different from the unity. So we can conclude that the duality defect is non-invertible. So this is rather one of the rare example of non-invertible symmetry in 4 dimensions. And we also calculated the so-called crossing relations. This is kind of similar to the algebra of the symmetry. And if you don't change the topology, then the defect has the same expectation values. And this crossing relation tells us if you change the topology, how correlation function changes. For example, if you change this topology to this way, then it's multiplied by 1 over square root 2. And the one interesting one is this one. In the left-hand side, we only have a duality defect, but in the right-hand side, we also have this Z2 center symmetry defect. So this duality defect by itself is not closed under this algebra or crossing relations, but it must include this Z2 symmetry defect. And combined with these two defects, the crossing relation is closed. And by using this crossing relations, we can calculate the expectation value of some defect. For example, this one. We apply this relation to here. You get this square root 2 times this one. And actually, this has a topology S3. So we use this result here. Then it is equal to 1. And although this maybe it's related to Nishoka-san's questions, although this is has a expectation value 1, it does not imply this. This is a counterexample. This is equal to 1, but this defect is non-invertible. Okay. So let me summarize. Today I talked about a new symmetry. It's different from the traditional symmetry, but it's useful. In particular, non-invertible symmetry. And we study 4-dimensional D2 lattice gauge theory and find this, in particular, this duality defect is non-invertible. And these two is combined to be to have some closed algebra, which is kind of a generalization of 2-dimensionalizing model symmetry. And this symmetry will not. This symmetry is a symmetry of this special theory, but it will appear in various theories as Kramas-Vanni duality in 2 dimensions. Kramas-Vanni duality is a duality of Ising model, but such symmetry appears, for example, in a tricritical Ising also and other models. And there's some discussions, and more recently, that these people found that there are a lot of examples of such non-invertible duality defects in 4-dimensional continuum quantum field theory. They use that picture gauging defect. And these because there are a lot of such continuum example, so it should be useful to invest this symmetry. This non-invertible symmetry should be useful to analyze those continuum quantum field theories. And another issue I'm interested in is the ADS-CFT correspondence and string theory using this symmetry. And we anticipated that, and they clarified that the duality of n equal 4 super-M theory is non-invertible actually. There is strong weak, say, Montan Olive duality here, but that is non-invertible for SUN gauge theory. And this n equal 4 SUN super-M theory is related to the type 2B string theory. So maybe there's some mechanism that, of course, duality of type 2B string theory is, for example, the SL to Z or something, and it's group symmetry. But once you introduce a boundary, then this shows that it becomes non-invertible by introducing the boundary. So I'm interested in how this becomes non-invertible when the boundary is introduced. And the related works are, this is old work by Witten. It's he discussed duality and ADS-CFT correspondence. And a more recent paper, anomaly for the duality of type 2B is discussed by these papers. And both of them, the topological term in ADS5 spacetime plays a crucial role. And due to that topological term and with boundary, I bet this duality becomes non-invertible. And in particular, I want to derive the circle or sphere expectation value from the ADS point of view. Okay, thank you very much. I stop here.
Yeah, it's time for questions or comments.
Well, I have a question.
Yes, please.
So have you considered the Hamiltonian version of your constructions, and maybe in the 1+1D I think case, does such a construction already exist?
Yes. Yes, that's interesting problem. And so far, I did not construct it. And maybe just because some lack of knowledge about in the 4-dimensional gauge theory, in order to construct a Hamiltonian language, maybe we have to do some gauge fixing or something like that one. So I don't have enough knowledge about that one, and so far I do not have Hamiltonian or transfer matrix construction in 4 dimensions.
Okay, how about 1+1 dimensions?
1+1 dimensions, the Arsemon Fendry paper, they did. Yes.
I see. Okay, thank you.
Excuse me.
Yes.
So in the last part, so you showed that the expectation value of the defect depends on the topology. So when you consider sphere type, then it is not equal to 1. But if you consider torus type, it becomes 1. So, so is it a general feature of such a non-invertible topological defect?
You mean this one is general?
No, I'm asking so why it depends on the topology of the defect.
Yes. For invertible defect, such thing is always 1, because this one is boundary of the inside, and this one is also boundary of something. So it is 1 for invertible symmetry. But the topology, non-invertible symmetry defect is topological. So by continuous deformation without changing the topology, it does not change the value. But once you change the topology, the value changes. That's a general feature of the non-invertible defect. Yes.
Thank you.
So you're saying that this duality of the n=4 SUN Yang-Mills theory is non-invertible. The duality you mentioned is the S duality, the electromagnetic duality, or something else?
Right. That one, S duality, or weak strong duality.
I see. So
And
what's the consequence of this non-invertible duality then? Does it tell you something about the phase of this n=4 Yang-Mills theory then?
Yeah, for n=4 Yang-Mills theory itself, we know that it's a conformal field theory.
Mm-hmm.
So we do not find any further consequence. But if you have some, say, for example, some deformation, relevant deformation, which preserve the duality symmetry, then you can talk about something about that theory. But I'm not quite sure that there is some relevant deformation which preserve the duality.
So can we see this non-invertibleness of this the duality from this S duality world expectation value? I mean, we can compute the S duality. So suppose that we can place the n=4 Yang-Mills theories on sphere.
Yes.
Then place the S duality world on
Yes.
the equator. Then we can
Yes.
compute that from
Yes.
there. Can we see the non-invertibleness?
Yes. The expectation value of this sphere expectation value is known. This S3 is 1/√n. If this is 2, this is 1/√2. And for generic n, this is 1/√n. And this is not equal to 1.
So it's a non-invertible. Okay.
Right. It's non-invertible. And I wonder this value can be derived from the ABDS safety point of view.
Or localization.
No, this is much easier than usual, say, defect, like Wilson loop or other more non-topological defects. It's topological, so you can discuss some more topological way, and you can derive this one by such discussion. So there's not you don't need very difficult calculation.
Can I ask another question?
Yes, please.
So I think you were studying the self-dual point.
Right.
In the coupling, in the space of coupling constant. But you said that the transition is first order.
Yes.
But doesn't this mean that the theory actually depends on the direction of the limit you take, whether you approach the self-dual point from the right or from the left? Are you actually considering a unique theory?
Theory is unique, but there's distinct phases. So it's like water and water vapor, and that two phases at the there is two phases at the same time. So there are so let's go back to that. At this point, the confinement phase and deconfinement phase exist at the same time.
Right.
Yes.
But then you computed the expectation values of the defect. So these expectation values are for which phase, water or vapor?
In some sense, that one is the defect between them. So,
but between. So I thought that this is not really very defined. No.
This is, for example, outside of this is confinement. This is.
Oh, I see. So you have a bubble actually.
Yes.
I see. Okay, thank you.
More questions? Comments? If not, let's thank the speaker for this wonderful talk.
Thank you very much for the attention.